Hello everyone and welcome. In this video we will be discussing how to design a job scheduler. What is a job scheduler? It is a system which accepts jobs from clients and it executes these jobs based on the schedule provided by the client. Okay. So let's say there is a client and it gives a job which is to be scheduled every day, which is scheduled for executing every day at 6 p.m. So the responsibility of the job scheduler is to execute the job submitted by client every day at 6 p.m. Okay, this is what a job scheduler is. Now in distributed scenario, what will happen? This is a simple job scheduler, but what if there is job scheduler and there are millions of clients? The client number is in millions. In that case, a single machine, a single job scheduler won't be able to schedule jobs. Okay, so that's why we need a job scheduler, distributed job scheduler, basically which can distribute the job given by client on multiple machines. This is what a distributed job scheduler is. Okay, when we say distributed, we are talking of order of millions. Okay, there are going to be lot of jobs, there are going to be lot of host machines on which the jobs are going to be scheduled. So we need to design job scheduler for such kind of system. Okay, let's see what are the functional requirements for such kind of job scheduler. Okay, first thing is that it is a scheduler. So whatever job is going to be submitted, it can be it will be scheduled either once or it is going to be scheduled periodically. Okay, it could be a one-time job or it could be a job that occurs at regular intervals. So that is what is meant by once or periodically. Okay, next is that after a client has submitted job, it can be cancelled also. So our system should provide this capability to client that the job that has been submitted, it should be cancelled also, like he should be able to cancel this job. Next is whatever job is being submitted by the client, he should be able to see status of those jobs. The status could be the job is queued, the job is running, the job is completed, or the job has failed. So the client should be able to see all these statuses also. Then there should be no concurrent execution. So as we discussed, there are going to be a lot of host machines, right? So the job scheduler should not, like the job scheduler should make sure that a single job is not scheduled at the same time on two different machines. Okay, it should make sure that a job is scheduled on a single machine only. And the job scheduler, of course, we have discussed that it should be able to handle multiple worker nodes. So these are the functional requirements. Now let's look at the non-functional requirements of the system. Okay, so we have already discussed the system should be able to handle scale. Okay, we are talking about the jobs that are going to be in millions. So maybe per minute there are going to be tens of thousands of jobs that are going to be given for scheduling. The system should have high availability. Okay, if a host node or if a worker node fails, then the job that was supposed to be scheduled on that worker node or that is currently running on that worker node, it should be given to some other worker node. Okay, then the execution result should be consistent. So we had already discussed that there should be no concurrent execution of jobs. So at the same time, a single job should be given to one machine only. So if this is ensured, the results would be consistent only. So let's say if a job was running on machine M1 and machine M1 somehow breaks down, so this job is moved to some other machine that is working fine. So the result of this job should be the result, actual result. It should not be mentioned as failed. Okay, after running it on other machine, whatever result is present for that job, it should be reflected in the same way. That is how the result should be consistent. Now let's see how would the high level design of the system look like. So we have multiple clients, there are a lot of clients, and how would these clients enter into our system? They would get entry into our system using API gateway. Okay, so this is our API gateway. This is our API gateway, and API gateway also acts as load balancer or a router. So it will redirect the API request to uh, the appropriate services. Okay, so this is the entry point to clients in our system. Okay, then there is a job submission service. So whenever a client comes and he wants to submit a job, it will be handled by the job submission service. Okay, so we'll look into what this service does. Then in order to store data about the jobs, we'll have a data store. Then whatever jobs are submitted here in the data store, that are going to be scheduled, right? So in order to pick the jobs from data store and schedule it, we'll have a scheduling service. Okay, now whatever jobs are being picked for scheduling, these jobs are going to be in millions. Okay, so in order to so there is an another service which would be responsible for executing the jobs, that would be job execution service. Now the jobs that are being exchanged between job submission service and job execution service are in millions. Okay, so we cannot have synchronous communication between scheduling service and execution service. Why? A scheduling service cannot wait for the execution service to respond with the result of the job, right? The job can take a few minutes to run, a few minutes to execute completely. It can take half an hour also. Okay, so job scheduling service cannot keep waiting for execution service to return with the results. So that's why in middle we'll need something that helps us give asynchronous communication between the scheduling service and the execution service. That's why we have a distributed queue in middle. So our job scheduling service submits all the jobs in the distributed message queue, and the job execution service picks all the jobs from the message queue and executes them, and later it will return the results. So this is the high level design. Let's see what all these services are going to do. What are the responsibilities of all the services we have discussed here. Okay, so we saw there is a job submission service. Okay, so job submission service provides interface for system to submit jobs, cancel jobs, and get updates on the job statuses. Okay, these are all the things that job submission service is going to do. What all things will submission service accept? It will first of all accept what the job is. Okay, what I mean by job, the job is going to be in the form of binaries or artifacts. That is what are going to execute on worker machines, right? So first thing that it accepts from the client is the payload. Payload consists of binaries and artifacts. Okay, so that is the first thing that job submission service accepts from the client. What other detail does it need? It needs the execution time. At what time in a day do you want this job to be executed? So next it accepts is execution time, and it also needs frequency. So is it a one-time job or is it a repetitive job? So the submission service also needs to know this. Okay, so these are the three things that submission service accepts from a client in order to schedule the job. Okay, then there is a job scheduling service. What does job scheduling service do? It picks the jobs that are to be scheduled next. So the job scheduling service decides a time interval, and in that interval it will pick the jobs from the data store, the jobs that are stored in our data store, and it will schedule them. Okay, so this is what a job scheduling service would do. Next, whatever jobs it has picked, it will push all those jobs onto the distributed message queue. We have discussed why it will push it onto the message queue, why it will not directly give it to the job execution service. Okay, the third service is job execution service. So job execution service fetches the jobs from the queue. It will fetch the job from this queue, it will execute the job on the worker nodes. Okay, so this job execution service consists of worker nodes. It will give all those jobs to the worker nodes, and then it pushes back the result onto the job store. After the job is done executing on the worker node, whatever the results are there, pass, fail, or whatever logs it generates, it will push all those results onto the data store, back to the data store. So this is the high level design of a job scheduling service. These are the things we'll require. Okay, now let's have a look at what all data will we need to store. Okay, so first what we saw, the client submits job details to the uh, job submission service. What all things was it submitting? It was submitting the frequency of job, the execution time, and the binaries or artifacts. Okay, these three things we had already discussed, but along with that we also need to store the job ID. It could be an incremental field, so with every job we'll need a incremented job ID. Okay, we also need the client ID. We need to remember which client had given that job. So these all are the things that we need to store in the job table or job store. Okay, then we discussed that the scheduling service is going to pick some jobs that are going to be run at regular intervals. Okay, so where will it store these jobs? It will store it in the schedule store. So it picks the jobs that are going to be run next, and it will save the job ID, next run time, so the time, the short period of time in which it is going to execute the job. It will need that next run time. Let's say it was scheduled at 10 a.m. in the morning, and after 10 a.m. it is to be executed at 2 p.m. In afternoon. So just before it is going to be 2 p.m., there would be a small time interval, let's say 5 minutes time interval or 1 minute time interval. So just 1 minute before the it turns 2 p.m., so at 1:59 p.m., the jobs will be fetched from the job store, and they will be stored inside the schedule store. Okay, and it will save the time when it is going to be run next, and it will also save the time when it was last run. Okay, if the job is scheduled for the first time, then this value, last run time, would be null. Okay, and next run time would be whatever time it has to be scheduled. Next we'll need the execution store. So whenever a job is picked from the message queue by the execution service, it will have to store these results. What I mean by results is it will have to store on which worker node was the job submitted, and at what time was the job submitted. So it will need to store the execution ID. It will also be an incremental field. Then the job ID, so it needs to identify in what execution what job was scheduled. It will need to store the worker ID, on which worker the job is executed. It will need to store the start time, when the job was started. It will need to store the status, so based on the execution it will need to store the status of the job, if it is being run, or if it is being if it has failed or something. Okay, and if the job fails, then it will also need to store the try count. So try count is the number of times the job can be rescheduled in case if it fails. Okay, so it will store the try count. It can also store the end time of the job, and it can also store the max count of the job, so maximum number of times the job can be rescheduled after failing. Okay, so based on our requirements we can store these two things also. Okay, next we'll need the list of worker nodes. So we'll store the worker ID. we'll need to store the IP address, because the execution service needs to push the binaries and artifacts, and it needs to know the IP address to communicate with the worker nodes. Then we can store the capacity of the worker nodes, like if our job is like if it is a standard job, we know the details of the job, then we can store how many such jobs can be scheduled on this particular worker node. So that becomes the capacity of the worker node. And we can also store the status. What is meant by status here? We need to know if the worker node is live or not. Okay? We need to be sure that the worker node has not gone down. So we can store the status. Along with this, we can also store when was the last heartbeat we had received from the worker node. So heartbeat is something that is used to ensure that the worker node is live. So we can save heartbeat also on worker in the worker list. And the last is the result store. So in result store, we need to store the execution ID, and we need to store the results of the job that was executed. It could be in terms of logs, or it could be, it depends on the job, what result it would produce. Usually it is logs only, so we can store these logs also. So these are all the things that we'll need to store while designing the service. Okay? So we now have a high level idea of how our service looks like. Okay, now let's discuss the details of this service. How would the job submission service, job execution service look like in depth? Okay, the very first thing we need to discuss is what should we be using. Should we be using SQL or NoSQL? Okay, so what are the characteristics of the data that we are going to store? We saw that it is pretty much structured data. Okay, the structure of the data is not going to vary a lot. Okay, then there are no complex join queries. So this while you are running through the data to produce some results or something, there are not going to be any complex joins. Okay, so we will not have to get data from multiple tables while reporting something. Okay, so that is what is meant by we don't need complex join or complex queries while fetching something from our database. Then the amount of reads and writes is going to be equal only. The number of jobs that were scheduled will need a result for all those jobs. The amount of reads and writes is going to be the same. And because we are designing for scale of millions, we know that the volume is going to be very high. So the data should be scalable. It should be able to handle million queries in a day. Okay, so we need our database to be scalable. Now if we look at these characteristics, the storage requirements can be handled both by SQL and NoSQL. Okay, but we need very high throughput. Okay, we need very high throughput for both read and write, and SQL will not be able to, or it is the right way of saying this is NoSQL will be able to handle these characteristics better than SQL. So whenever we talk about large scale, the throughputs the throughput of NoSQL databases is going to be better than SQL databases. Okay, so that is why we choose NoSQL database. Okay. So NoSQL would be good for all the things except the binaries and artifacts. The binaries and artifacts are object files. Okay, so we'll need to store them in a blob storage or an object storage like Amazon S3. And the place where we mentioned binaries and artifacts, this binaries and artifacts would actually be linked to the binaries and artifacts, and the actual binaries and artifacts can be stored in an object storage like S3. So in S3 the binaries would be stored, and here we'll store the link to these binaries, the link of object storage where the binaries are present. Okay, so we'll use NoSQL database for storing our data. What NoSQL database can we use? We can use here DynamoDB or Cassandra. Okay. Now let's look into the services in depth. Okay, the very first service that we saw was scheduling service. So what does scheduling service do? Scheduling service picks jobs from the schedule store. Schedule store was a table, if you remember. Okay, I'm using the word table for all the things that are present here. So I would be saying them tables, but you need not confuse yourself. We have already established that we will be using NoSQL database. I'll just be using table for convenience. They are not actually being stored in the form of tables. Tables are stored in NoSQL. In SQL. So we are using NoSQL database here. Okay. So we saw the schedule store. The scheduling service is going to pick jobs from the schedule store that are going to be run in next interval. So during peak hours we are going to have thousands of jobs in a second, right? It will be difficult to handle this scale by a single node. If scheduling service is running on a single node, it would be very difficult for the that one service, that one particular machine to handle thousands of jobs, right? So single node running a scheduling service won't be sufficient. So that is why we'll need multiple nodes. That is one thing. Moreover, if we have a single node running scheduling service, it can become a single point of failure. So we definitely don't need a single node running scheduling service. We are going to need multiple nodes. So in order to have multiple nodes, we'll have a system something like this. So there are multiple worker nodes that would be running our scheduling service, and there will be one coordinator that manages all these worker nodes. Okay, then with this kind of system there is a problem. How will we ensure that the job is picked by a single worker node and it is not being picked by multiple worker nodes? We have a job store, so there is a job store we discussed earlier. How do we ensure that the same job is not being picked by multiple worker nodes? To ensure this, we'll introduce one more segment in our job store, one more column in our job store. We'll name it as segment. Okay, and we'll number the jobs according to segments. So let's say we have n worker nodes, so we'll divide our jobs present in the schedule store in n segments. So 1 to n. Now each worker node picks a job from a specific segment only. So we'll map each worker node to a particular segment, and that worker node will pick job from that segment only. So this is how we can ensure that the job is not being picked at the same time by two different worker nodes. Okay. Now let's look at the execution service. So similar to the scheduling service, execution service also cannot handle multiple jobs at the same time, right? So in the execution service also we will have a coordinator node, and we'll have multiple worker nodes. This we had already discussed, that we'll need multiple worker nodes on which the jobs are going to be scheduled, because there are lots of jobs. Okay, so let's discuss the responsibilities of coordinator node and worker nodes in the execution service. So coordinator picks the jobs from the message queue and assigns them to the worker nodes. Okay, then it keeps the check if worker nodes are live or not. Okay, how does it keep check on that? The worker nodes would be sending heartbeats at regular intervals, and if the execution node does not receive 3 consecutive heartbeats from the worker node, it will assume that the worker node is down. So that is how it keeps check if the worker node is live or not. Okay. Then in case if the worker node goes down, it will reassign its jobs to the another node. Okay. So in case if the job it was executing some job, we'll need some kind of checkpointing mechanism to make sure until where the job was executed, and from there on the job could be picked like or executed from the another fresh node or healthy node, which the coordinator will put the failed job onto in case if the worker node goes down. Okay. In case if the job was about to be executed on the worker node and the worker node is down, then it will be simply reassigned to some another worker node, healthy worker node. Okay. It also the coordinator node also does the load balancing between the worker nodes. It schedules job on worker nodes in such a way, or it distributes the job on worker nodes in such a way that the load is equally distributed among them. Okay. Then there are worker nodes. So it starts the job, starts executing the jobs that are assigned to them. It keeps updating the status of the jobs which are being executed. If a job fails on itself, so let's say a job could fail because of various other reasons also, the process could crash. Okay. So in that case the worker node is still healthy but the process has crashed. So in that case the worker node will again retry the job. Now it will not keep on retrying at regular interval. It can retry after double the time it has retried. So let me explain this with the help of an example. Okay. Let's say there is a job that is currently running and it fails. So the amount of time after which the worker node retries for first time would be, let's say, 2 minutes. Okay. After 2 minutes it retries the job and the job fails again. So before retrying next time it will wait for 4 minutes and the job fails again. So next time it will wait for 8 minutes. So it will keep exponentially increasing the time to retry the job. Okay. Okay. Next thing is that if the job is successful, it updates the result of the successful job back into the result store. Okay. And it keeps sending, we had already discussed that it keeps sending heartbeats to coordinator nodes at regular intervals. So that are all the responsibilities of the worker node. Okay. Now let's identify what could be single point of failures in this particular system. So in the job scheduling service and job execution service, we saw that there was a coordinator node, but we have mentioned that there is a single coordinator node. There are multiple worker nodes, but coordinator node is one only. Okay. So this coordinator node could become single point of failure. So how do we prevent this from happening? We can also have multiple coordinator nodes. Okay. We can set some number and these coordinator nodes would be present on different networks or in different regions. So these coordinator nodes, amongst all the coordinator nodes, one is going to be active coordinator nodes and others are going to be passive coordinator nodes. Why do we need them in different regions or different network or on different power supply? If because of some reason one node fails, let's say there is power cut and one node fails, coordinator node fails, then we can make sure that the other nodes which are on different power supplies would still be live. That is why we will have them on different networks or different power supplies. Okay. So amongst all the coordinator nodes, one is going to be active and others are going to be the passive coordinator nodes. Now in case if the active coordinator node fails, a leader election algorithm kicks in. Okay. That leader election algorithm will make one of the remaining coordinator nodes as the leader and others are again the passive coordinator nodes. and the since the data is independent of the worker data is independent of these machines, so the data which we are storing is not present on these machines, so they all of these share same data. So a coordinator node can pick from where the last coordinator active coordinator node left. So there is no problem of how would and how would a passive coordinator node that has just become leader resume its activities. There the data is present on different nodes and different servers, so it can still read from the data is still intact. Okay? In order to elect the leader, there could be like based on use case you could pick any of these algorithms. There is ring algorithm, bully algorithm, paxos, or you can use zookeeper also for electing leader. So zookeeper handles that for you, so you can use zookeeper for the same. Okay, so this is pretty much it. I hope you would have understood this. um, Stay tuned to this channel to get more of these videos. You can subscribe to the channel to get updates whenever I upload the video. I hope you would have enjoyed this video. Thank you so much.